Hello, this is Jack Jackson. In this video, we're going to introduce the concept of a surface integral, also known as a flux integral. So just as we can give an orientation to a curve, which by the way is defined by one parameter, we can also give an orientation to a surface, which by the way could be defined by two parameters. We know that what we mean by normal vector to a surface, it's perpendicular to the tangent plane at the point on the surface. And there will be two opposite choices of direction for each of these normal vectors. If we choose them in such a way at each point on the surface to make them continuously change, then we have chosen an orientation for the surface. For example, if the surface is a sphere, then the two possible orientations are into the sphere, vectors are pointing toward the origin, or out of the sphere, but normal vectors are pointing away from the origin. So those are our two orientations. So a surface or flux integrals, one way to think of them is by measuring the flow through a surface. So for example, we can take a surface such as a net or maybe a coffee filter, which was placed in the flow of liquid, say a net and water or a coffee filter in a coffee machine, and liquid flows through that, and we could be measuring how much the flow of the liquid is through that. That's the basic idea of what's going on in a surface integral. So here's an example of a pipe that's in a square cross-section shape. We've got a grid that's running across there, a mesh grid. It's kind of at an angle here, and the flow of this liquid is coming through that grid here, and these vectors represent the velocity of that flow. And we could somehow measure how much is going through there. And that's kind of the basic idea of a flux integral. In another sense, the surface integral takes the concepts developed for line integrals and then bumps them up one dimension. So to begin the setup for defining the surface integral, we need to subdivide the surface into smaller and smaller subsurfaces. Each of these may be approximated by the interior of a parallelogram in the tangent plane, and let delta A be the area of this parallelogram. We convert this to a vector by multiplying by unit vector in the direction of the surface that is perpendicular to the parallelogram, when we call this vector delta A vector. If we have a velocity vector field V represented by the velocity of the flow of a liquid, like in the picture before, then the flux or flow through that piece is approximated by the velocity vector dotted with this area vector. We can sum these values up and take a limit to obtain a surface integral. So we'll define a surface integral integrating over a surface f dot dA as the limit as n goes to infinity and the norms of these delta a's go to 0 of f sub k, that is the f evaluated at different points on the surface, somewhere in that little sub region, okay? And then delta A vector, we want to dot product those two together, sum those up, and that will give you a flux or surface integral. This little dot product here will give you an estimate or a rough estimate of what's happening as far as the flux through that little piece of the surface. Again, that's an approximation because we're approximating the surface with a parallelogram, and then we're assuming the force or the flow vector F is a vector field that's constant on that piece. But if you break this into smaller and smaller pieces, that approximation, once you sum it, becomes closer and closer to the thing we're looking for, and the limit makes it exact. Pretty typical thing that we do with integrals. So notice that the domain of a flux integral is a surface, and the surface might be given in the form of a parameterization using two parameters. In a similar way to which we are able to rewrite a line integral in terms of a single integral of the parameter, we can rewrite the flux integral into a double integral in terms of the two parameters. The key to this is to notice that we can approximate the area vector of one of the subpieces as the cross product of the two vectors along sides of a little parallelogram from the tangent plane. And remember that the cross product of two vectors is a vector with the area being the area of the parallelogram is the magnitude, and the direction is perpendicular to both of these vectors. So here we have this is a little piece of the tangent plane that we're approximating the surface with, and say it's tangent at this point right here. Then this vector is the partial derivative in the t direction. So I'm going to call that sub t really is a partial derivative there. That's partial with respect to t. It's actually this thing right here. And that's going to be the sort of the slope in that direction. You multiply that by delta t, you're going to get the length of this vector here, at least in this tangent plane. Similarly, we take the derivative, partial derivative that is, of the r function with respect to u, and multiply by delta u to get that vector there. Okay, these are vector derivatives, so these are vectors. Multiply those together, that is a cross product, and we get a vector which has this parallelogram as area, but the vector is going to be pointing out perpendicular to this plane. So the delta A vector is approximately the dot product of those two things, and notice these are the delta t and the delta u are scalars, so I can bring that out to the end here and just do the cross product of those two vectors, r sub t and r sub u. A better way to write those would be the partial derivative with respect to t of r, cross product the partial derivative of u with respect to r. And then we have a delta t, delta u. Now, if we add those up, take a limit, then this delta u and delta t here becomes dt and du. This is our cross product here. And then we're going to integrate our function f here. So basically, the dA is replaced by this cross product and then the dt du. And then the f, of course, is probably given to you in terms of something else, like an x and a y maybe, or x, y, and z, 3D. But it's you want to get it in terms of your t and your u. So you just do a substitution there. So let's look at an example here. Suppose we evaluate the surface integral, the flux integral, of the following vector field through the given surface. So S is oriented downward. S is given by R, the position function of TU, those variables, parameters, as TU, comma, U plus T, comma, 1 plus U minus T. And we're going to let T go from 0 to 1, and U also go from 0 to 1. And that defines a surface. So it actually turns out to be a portion of a plane. And the vector field is given by x, comma, y, comma, 0. And we want to find the flux there. So what we do here is we just do our parameterizations, right? So we've got, here's the S parameterization that was given. The partial derivative of that with respect to R is take the partial derivative of each component with respect to, of R with respect to T. So the derivative 2u with respect to t is just 0. The derivative of u plus t with respect to t is 1. And the derivative of this last part is 0 plus 0 minus 1. So it's 0, 1, negative 1. Turned out to be a constant vector this time. Very often that might be a vector that's in terms of u and t, both. Similarly, when we do the partial derivative of that r vector with respect to u, we're going to get 3 components. The derivative of the first part with respect to u is 2. The second part, the derivative with respect to u is 1. And the last part, the derivative with respect to u is 1. So that's the vector 2, 1, 1 for that derivative. Now what we want to do is cross product these two vectors. Say if we do the t first, then the u. Okay, then we put the t vector here and the u vector here. One of these directions or the other will be oriented the right way. We're going to orient up, so we want the one with the positive, we want it oriented downward. We want the one with the negative z component, k component. So here's the cross product. Write those here and here, expand by minors. Hopefully you guys remember how to do the cross products. There are the details worked out, and that is also a constant vector, 2, -2, -2. Again, in a more general setting, this might have U's and T's or both in it. Now our vector field is x, y, 0. You rewrite that in terms of U's and T's. The x is 2U, that's our parameterization, so you replace that. And the y is U plus T, so we replace that as well. Then we're going to need the dot product of the F and this cross product here. So you put this guy here, in terms of U and T, dotted with this one up here. So that's pretty easy. You just take the first term times the first term, that's 4U, plus the second times the second, so it's -2U minus 2T. And then the last part, 0 times -2 is 0. 4U minus 2U is 2U, so that dot product of the cross product is, and another vector, is the 2U minus 2T. So that's the function that we want to integrate. So notice that we've finally boiled this down to a double integral in 2 variables like we had done earlier in the course. Got everything in terms of our parameters U and T. Now since T and U are both just going from 0 to 1, that makes the limits here pretty straightforward and pretty easy. And well, let's just work this out. We take the derivative, antiderivative with respect to U. That goes up to the second power and divide by 2, so that's U squared. That one picks up a U as a factor. Plug in 1 and 0 for U values. So this is 1 squared minus 2T times 1, that's right here, minus, then plug in U's 0 here. The 0 ones here wipe out to be 0, and this is just 1 minus 2T. Take the antiderivative of that with respect to T. It's T minus T squared. Evaluate from 0 to 1, plug in 1s, plug in 0s, subtract, you get 0. So this is actually 0. Here's a picture of it. Here's the little portion of the plane. And we do have vectors coming in and out of this plane. The ones going downward through this are going to add to the flux. The ones going up are going to subtract from it, and the ones tangent to it aren't going to have any effect. And in fact, the amount going in, the amount going out balance in this case, which is why we had 0 for that answer. So there's a quick introduction to flux integrals.